I'm Joe. I'm a geologist at the University of Liverpool, and this is my field area in northern Italy. It's really, really nice. It's on the edge of the Alps. So let's get started. So I study in the Rock Defamation Lab at Liverpool. But what exactly is rock deformation? Well, it's kind of what it says on the tin. It's the way that rocks, and so the material that makes up the Earth, deforms. And there's several different ways to study this. There's three main approaches, and often people have a merge of several of them, or one or two, or just a single one. Firstly, you can do experiments, whereby you directly kind of study the processes in a lab. But this requires quite a lot of extrapolation to nature. So you can't get to the kind of pressure and temperature conditions in a lab that obviously you do in the Earth. And also the rate at which things deform the Earth is often much slower than you can realistically do on an experimental timescale. Secondly, you have numerical modeling. So that's exactly, I mean, a lot of you are numerical modelers. I don't do any of that, so you know a lot more about it than me. But essentially, you can predict lots of processes at lots of scales. You can do a lot of interesting things, but it's often it's often slightly simplified. You make some assumptions relative to the actual natural systems. So it's a bit of a trade-off there as well. And then there's natural observations, and this kind of captures all the complexity of nature. You go out in the field and you look at the rocks, you look at the microstructures, but that's a pro and a con because it's incredibly complex, and you just are trying to look at basically a dog's breakfast and trying to work out what happened. So I actually fall in the third category here. I do natural observations. I go out in the field and I try and look at the evidence and work out what's happened in the past. So you can think of it a little bit like Inspector Clouseau or just any sort of crime drama. You see the crime has happened and you've got to piece together everything at the scene and work out what's happened before. Unfortunately, we don't have a baddie who tells us the answer at the end. We just have to try and prove it. Okay, so what sort of things do we look for? Well, you look for structures because they can tell you about the way that the Earth deforms. It's very important to understand how the Earth deforms because though it looks to us like the mountains and ocean basins are just there and they've always been that way, it's really not the case. The Earth, just like the atmosphere and the oceans, are a dynamic system, and it's constantly changing, and it has feedback loops that impacts everything else on Earth. So going back to this slide, there's you can look at the structures you see in the rock to tell you about the types of deformation. So just as a very kind of simple example, you can have brittle failure in a fault, and many of you might have heard about fault lines, and that's that's just brittle, what you imagine rocks doing. That happens very near the surface. But you can also have viscous deformation of rocks, and this is kind of counterintuitive. So rocks can deform like this and kind of have folds and plastic viscous deformation without necessarily melting. So they just deform very, very slowly at very high pressures and temperatures. And you can think of it a bit like putty. That's not a liquid, but it can deform in a kind of plastic way. And this is the kind of side of things that I look at. So rocks that have deformed much deeper in the Earth. And then on a finer scale, you can look down through small samples and through microscopes, even down to work out the mechanisms that deformation has occurred on a micro scale. For instance, things like how dislocations, which are little defects in the crystal lattice, move through the crystal lattice in mechanisms such as dislocation creep and diffusion creep. I won't go into what those are today, but I'm just letting you know as broad spectrum you can look from very large scale things, from mountain belts right down to working out what's going on an atomic scale. So focusing now on my project, I focus and I work very much on a mineral called mica. It's a group of minerals which are phyllosilicates, which means they're sheet silicates. So these are not bits of plastic. These are actual mica crystals. Mica's they look like this with these kind of flaky, very thin layers. Because of this is their atomic structure. You can see here, this is looking down the layers. You've got one layer of tetrahedra and octahedra, and then you've got an interlayer. You've got a region of interlayer cations here, which is weakly bonded to another layer here. So these minerals often were called Mica Books. That's the actual term for them, because when you pick up a piece, you can flick through the flakes a little bit like the pages on a book. And what this means, why they're important, is because this makes them incredibly weak. So this particular layer here in the crystal structure is very weakly bonded. And that means that if you were to deform this mineral, not so much like this, but if you were to shear it this way, it's like jam in a scone. If you break it that way, it's very easy easy to deform. So they're very, very weak minerals. And that's important because even if they're at a small concentration in rocks, the fact that they're the weakest phase there means that once they can connect and form a network within that rock by deformation, they can take up a lot of the strain. So if you, again, going back to that scone model, if you have a solid, or maybe a sandwich, if you have a solid piece of bread and then something like butter in the middle and then another solid piece of bread, you don't need to break the bread to deform that sandwich. You can focus on deforming the weakest mineral. So that's why mica is very important. And I'm trying to work out the mechanisms and the ways in which mica deform to understand a little bit about deformation on the crustal scale. So this is my field area in the north of Italy on the edge of the Alps, just to show you where I work. And I work on a shear zone called the Cassato-Magozzo-Brissago line, or the CMB line, much easier. And what I mean by a shear zone is it's like a fault zone, but when it gets deeper into the crust and you get plastic deformation instead of brittle deformation, we often refer to it as a shear zone. And in this case, it separates a region of the lower crust from a region of the upper crust, and that's how we know it was. It formed much deeper in the earth, and then when the Alps was uplifted, it was brought to the surface and eroded, and that's why we can see the plastically deformed rocks now at the surface. So I went there and I've done some mapping, and this is one of my maps of the area, and I found the shear zone running through here, and just some kind of outcrop scale observations. You can see these just about make out these kind of stripes in the outcrop here, and then at a smaller scale, you've got black and dark stripes here, and this is, and even down to the myelinite, which is the type of rock I work with, you get this clearly highly strained structure. So these stripes and these lineations mean that you've had shear in this direction, and you basically smooth, well, I was going to say smudge out the rocks, that's a very bad word, but you basically just, you basically, these have been highly sheared and highly strung out, and that's why you get linear features produced. And in this case, the darker regions are much more mica-rich, and on a first order, I found that the dark mica-rich layers seem to have undergone more deformation and incorporated more strain in this case. So I produced a transect in more detail produced several actually, but we'll focus on this transect along this part of the CMB line. So as you go through, you can see it's not a simple, this is the width of the shear zone, you can see it's just over 120 meters. There's a bit missing in the end because there's no outcrop, so I couldn't study that. But it's not a simple, you have not very much strain on one side, then high strain in the middle, and then not very much on the other side, like a fault. It's not just one slip zone. There's actually several regions and bands of very high strain interspersed with regions of lower strain. So for some reason, the strain, the degree of strain is being distributed heterogeneously within this shear zone. If we look at the microstructural change across different degrees of shear, you can see from lower strain, so the minerals to look at here are the darker ones, in this case the red and the green, they're the micas. You can see these are all the same rock type, but initially you have these quite large grains and large bands. Then this kind of lineation and interconnection becomes greater and greater as you move up strain until you get to the final very fine grain product. And the reason you can't see much red and green there is because it's very, very fine, and it's interconnected into like a big matrix. So you basically, the whole thing is quite well mixed. So what you're doing is you're connecting the weak phase, as I was describing, and you're concentrating more and more strain into mica. So there's an increase in biotite, particularly biotite is a type of mica connectivity with increasing strain. So what's the microstructure of that biotite? How is the mica deforming? Well, initially, so these are the same stages of strain as I showed you on the previous slide up here. So initially, the biotite is the dark phase in these micrographs. Initially, you have kinking and bending of the micrograins. So you've got quite coarse grains, quite large grains, and they bend and kink and deform that way. But then quite early on with increasing strain in the deformation history, you start to see, it's quite difficult to make out here, I guess, but here's a coarse grain, and here is lots of smaller grains of brown biotite. So you get some sort of breakdown, some grain size reduction in the biotite. It's no longer just large grains changing shape. It's actually they're breaking down to a smaller grain size. And as you increase in strain here, this is a coarse grain, but all of this around here is all very fine-grained material. And you can see how the lighter stuff is not deforming as much, but the finer-grained material is taking on a lot of the strain, until finally you get to darker material, much finer-grained material forming a matrix that forms the majority of the rock. So clearly there's a dramatic grain size reduction. But importantly, what's forming this grain size, this interconnection? What mechanism is allowing this grain size reduction to occur? So we need to get, we've got two potential ideas for that. Maybe you've got dehydration and recrystallization. So micas, especially biotite, are hydrous minerals. Within their crystal structure, they contain a certain amount of water. And if you heat them up or if you deform them, you can maybe lose some of that water, and that would cause them to break down and then recrystallize new grains afterwards. So this would be basically loss of the old grain, loss of the old structure, and formation of brand new strain-free grains. Or potentially segmentation. So this is another idea put forward specifically for minerals like micas with very easy slip directions. In this case, you actually are just breaking up the old grain into lots of smaller pieces. So they're still pieces of the old grain, and their internal deformation is still got the same signature of the old grain. So if we look, I'll skip through this slide. If we look down to some high resolution, this is TEM imaging now, transmission electron microscopy. So you can get down to some really fine resolution. You can see these it's actually quite amazing, because these stripes in here are actually on an atomic scale. They're these layers in the crystal structure I showed you earlier. And you can see some of them here. These strands here are actual atomic layers, and you can see this kind of voids opening up and this damage within the mineral structure. So this is an example of some damage internal crystalline damage. And what you can see here, this is a grain that's coarse, and then some of the breakdown product, and we caught it in the process of breaking down, as it were. This internal deformation, this internal damage, is present in all three stages of this deformation. So in the old grain, which you'd expect to be damaged internally because it's been kinking and bending, but also in the newer, smaller grains that we thought maybe they're dehydrated and recrystallized, maybe they're fresh grains. Well, actually, we see this kind of internal structure that hasn't been seen very much before is actually present in all stages. So that would suggest potentially we're looking more at the segmentation mechanism, whereby these are smaller pieces of this grain. So the next stage is to work out exactly how does that segmentation process occur. There is a future work slide, but I'll leave you on summary and conclusions. Thanks.